Hello students, today we are going to start a new chapter, that is types of molecular spectra. So you know that earlier in this particular course uh, we have studied atomic spectra. So basically you can divide this particular course in two groups, atomic spectra and molecular spectra. So this is a spectroscopy course. Atomic spectra part we have already completed. So in the beginning we have studied the atomic structure, then we have seen the spectra of the one valence electron system, that is both hydrogen and sodium. Then uh, next we have also studied the spectra of two valence electron system, where we have studied the spectra of helium. And then in the fourth chapter, we have studied an important effect in case of atomic spectra, that is Zeeman effect and Stark effect. And recently in the fifth chapter, we have studied the X-ray spectra or details about the X-ray spectroscopy. So all these things are related with the atomic spectra. Now after this, we are going in the second part, we are going to start the study of molecular spectra. So, in this particular lecture, I am just going to cover these 3 points. So, first, I shall discuss about what is molecular spectra. Then, second thing, I shall define the types of molecular spectra. And finally, we are going to study about rotational energy levels of rigid diatomic molecule. So, first of all, let us see what is actually a molecular spectra. So atomic spectra, we have seen that it results because of excitation of electron among its levels. So initially the electron, mostly the outer shell electron or the valence electron, which is in its normal state, which we call as a ground state. If it is excited to the higher state, higher energy state, and thereby perform a transition, so the transition may be upward transition or downward transition. During upward transition, you can think of the absorption spectra, or if we assume the downward transition from higher energy state, if the electron comes back to its ground state, the energy difference will be given out into a characteristic photon of certain wavelength, which is a characteristic wavelength of that particular element only. So that forms the emission spectra. So all that just introduction about the atomic spectra, what we have already studied about. So molecule, you know that. Now to know about the molecular spectra, first of all, let us see what is actually a molecule. So molecule is a group of two or more atoms. So basically the connecting force between the two atoms, not only two but more than two also. So there are some forces which bring different atoms together to form a molecule, where positively charged atomic nuclei will be surrounded by a cloud of negatively charged electron. So there are certain forces. For example, if you consider the simplest molecule which all of us know, H2O, okay, where two hydrogen atom and one oxygen atom. So this is the oxygen atom and these are two hydrogen atom. So see the attracting forces. So a covalent bond is formed between hydrogen and oxygen, because oxygen, you know that atomic number 8. So 2 electrons in the first shell and 6 electron in the second shell. So second shell, in order to be completed, it is short of 2 electrons. So it can borrow this 2 electron from hydrogen. So it needs 2 hydrogen atoms to form two bonds here or share 2 electrons in order to complete its outer shell and to become a stable. So this hydrogen atom forms a covalent bond here. It shares the electron. Similarly, this shares the electron and the water molecule is formed. So these are the attracting forces. Two bonds are formed here. Oxygen, hydrogen. Here also oxygen, hydrogen. And the electron cloud of oxygen will be actually reformed here. So these two are this electron, this one and this one, they are shared by two atoms, okay, and the remaining electrons, this pair of electron and this pair of electron, they form a lone pair. In chemistry, you might have studied that. Okay, so what just I want to point out that there are some forces acting between the constituent atoms of the molecule. Okay, so the attractive and repulsive forces of the nuclei and electron, they balances each other in order to form a stable molecule. So you know that molecule will be a stable only when these attractive or repulsive forces between the nuclei and electron, because electron of this atom and electron of this atom, nuclei of this atom, nuclei of this atom. So there may be force, attractive force between the positive nuclei of this atom and electron of this atom, or positive nuclei of this atom and electron of this atom. So both way this is possible. There may be repulsive forces also, electron of hydrogen and oxygen. Okay. So attractive and repulsive forces of nuclei and electron, they are balanced in a molecule in such a way that there is a lowest energy involved. Lowest energy of the molecule is involved, and the molecule will be stable in that case only. Okay. So a molecule is characterized by total energy, which is the minimum possible energy resulting from these interacting forces between the constituent atom. So that particular energy is important for us. So just like the outer electron, optical electron in an atom, it has the ground state energy, and when excited it can change its energy state. Similarly, molecule as a whole has its own resultant energy. Okay, so that is the minimum energy, so you can call that is a ground state energy of a molecule. So whether molecule can be excited, yes, just like atom, molecule can be also excited, and it can have discrete energy level. So by absorbing external form of energy, the molecule can change its energy state from ground state to higher energy state. So there are certain allowed energy states for molecule, and these energy states are also quantized. That means there are only certain discrete allowed energy states are possible for a particular molecule. So for different molecules, these energy states are different. Okay, so molecular spectra. Now let us come to the point, main point. Okay, so what is molecular spectra? So when we say that a molecule has different energy levels, discrete energy level, allowed energy level. So whenever there is a transition between these energy levels, you can say that the energy difference is given out or absorbed in the form of photons, and that forms a constituent set of photons which forms the spectra of the molecule. So molecular spectra results from either absorption or emission of electromagnetic radiation as the molecule undergoes changes from one energy state to another energy state. So these are the allowed energy state for a particular molecule. Remember. So you can say the molecular spectra, it is more complex than atomic spectra. Let me focus on this particular statement. What is this statement? Molecular spectra is more complex than atomic spectra. So let us see why it is so complex. Let us think about this. The complexity of molecular spectra is due to certain reason. So first and very important reason is that the interactions of the various nuclei with each other and with electron. So you know, molecule as I have defined is a group of two or more atoms. So different nuclei are involved there, and their surrounding electron cloud, you can say. So there are interactions among these different nuclei and these different corresponding electrons surrounding to them. And due to this interaction, different kind of forces are acting here. So there are different set of energy states, you can see, because of these forces. And second important reason is that different types of molecular motions and energies involved in this particular case. So because of the external energy which is received by the molecule, there may be different types of molecular motions involved, or you can say the molecule has different set of energies. Now, these also causes the molecular motion also causes the change in energy state of the molecule. Therefore, simultaneously, the forces, different force, interactive forces, different molecular motions, different energies involved, all these are having their own impact, and therefore, the energy states involved, there are different types of energy states involved in case of a molecule, and the simultaneous transitions among these different states results into different types of spectra for a molecule. So let us see what are these different interactions. Three possible interactions are there. So first is the excitation of electron in a molecule. Okay, so just now we have seen that molecule is a group of two or more atoms. Every atom has its own set of electrons, and when some external energy is received by a molecule, so individual atom, electrons from individual atom may be excited. Just like in an atom, electron are excited, so in a molecule, in a constituent atom, the electron may be excited. So you can say overall it is the electron from that molecule. So excitation of an electron in a molecule, this is the first, and very similar to atomic spectra kind of interaction. Then second one, it is observed only for molecules. Rotation of molecule about an axis. So because of external energy received by the molecule has certain symmetry, or you can say about certain axis, the atoms, constituent atoms, they perform a rotational motion. So because of this rotational motion, there may be change in energy states. And third one, vibrations of atoms about their equilibrium position in a molecule. So in a molecule, the atoms, constituent atoms, they are bound together because of certain forces. You can say the bonds. In chemistry, we use a term bonds. Okay, covalent bond, then a metallic bond, ionic bond, and so on. So these bonds, so you can consider a bond axis, and you have any axis of symmetry. So if you consider the rotations of these atoms about the equilibrium position in a molecule, uh, that will be a rotational motion. But if you consider the vibrations of the atom about their mean position, okay, so the distance between the atoms will change, and that will cause the change in energy state of the molecule. So these are the third interaction, vibration of the atom about their mean position. Then, so what is actually a molecular spectra? So different energy levels are involved because of the three interactions just now I have mentioned. So what are these energies? First of all, energy level due to electron excitation. Just like in atom, the minimum energy of an electron, ground state energy, and different energy levels. So in molecule also, each constituent atom has its own energy level due to electron excitation. Let us represent it by E small e. Suffix small e represented by the electronic excitation. Then second thing, energy level due to rotation of the molecule. Okay, the rotational energies involved in case of molecule. So every molecule has certain set of energy state because of its rotational motion. So let us denote these energy levels by ER. Small r represent the rotational energy level. Then third, energy level due to vibration of the molecule. So vibration, that is one of the interaction which I have mentioned. So vibrational energy levels do exist for a molecule. We can represent it by E small v. So V suffix used for vibrational energy level. Now these energies involved here because of the three typical types of interaction just now I have mentioned. If you compare the value of these energies involved here, then you can order them in this manner. So the electron energy level, energies involved in electron energy levels is more than the energies involved in vibrational level, and it is more than the rotational energy level. In short, the rotational energy states, they are having lowest energy values, whereas the electron energy levels, they are having highest energy values involved here, and the vibrational energy level, they are in between these two. So spectra of a molecule is more complex. Why it is complex? You can see here. So three type of energy levels are there, and in each type there are several energy states. So simultaneously there can be change, either one or two or three. Simultaneously, any number of states can undergo a change, and that result different set of lines. Therefore, the spectra of a molecule is more complex than spectra of atom because of these motions and the energies of the molecule. So this is what a very important thing we have learned about the uh, spectra. What is molecular spectra? So there are three interactions involved. Now let us define the types of molecular spectra. So as I have discussed here, the interactions involved. Now depending on these interactions, we have a three types of molecular spectra. So first one, pure rotational spectra. A molecule can possess a pure rotational spectrum only when electronic configuration of an atom and vibrational states of molecule remains the same. So let us try to understand this. So electronic configuration of atom remains the same means what? So electronic configuration represents the number of electrons in different orbitals, shells and subshells. Okay. So if the electronic configuration remains the same, that means the electrons, all electrons, they remain in their own level or subshell, whatever it may be. The position of electron do not change. They remain in the same orbital. That means here the electrons are not excited. In a molecule of the constituent atom, the electrons are not excited. Then second, vibrational state of molecule remains the same. So vibrational state remains the same. That means the atoms are not vibrating. So atoms are not vibrating. Then the electron from constituent atom, they are not excited. So what is the remaining? Third interaction only. The molecule is rotating about certain axis. So in that case only pure rotational spectrum can be observed. So this is the condition. Okay. And as I have defined earlier, there are certain allowed discrete rotational energy levels. So whenever there is a transition between these rotational energy states of a molecule with the emission or absorption of a photon, it will give rise to a pure rotational spectrum. So this is the first type, that is the pure rotational spectrum. So these rotational energy levels, they are separated by small energy interval. So earlier I have compared E small e, that means electronic energy level is greater than vibrational energy level and vibrational energy level is greater than the uh, rotational energy level. So rotational energy level is the lowest. So it is the small energy interval of the order of 10 raised to minus 3 electron volt. So it is very small amount of energy here. So rotational energy and the related spectral line appears in the spectra because of the transitions among the rotational energy level. They will lie in either microwave region or far infrared region. Most of the time in far infrared region. So far infrared, you know that infrared region of the electromagnetic spectra is approximately divided into three classes. Okay, near IR, then IR, and far IR. So far IR is larger wavelength in IR region. So this is the first type, pure rotational spectrum. Now let us see the second type, rotational vibrational spectrum. So the name itself indicates the two interactions simultaneously taking place. Earlier we have defined three interactions: electronic excitation, rotational motion involved in a molecule, and vibrational state. Okay, so rotational vibrational spectrum obviously will result because of these two interactions simultaneously. Okay, so what is the condition to observe rotational vibrational spectrum? The electronic configuration of an atom must remain the same. That means electron should not be excited. And then if the atoms are vibrating about their mean position, then the molecule is also rotating about the simultaneously about certain axis of rotation. There may be transition between the vibrational energy state of a molecule along with the rotational energy level with the emission or absorption of a photon that will give rise to rotational vibrational spectrum. But suppose if the molecule is having only vibrational state. That means the molecule is not rotating, only vibrational motion is involved. Then in that particular case, the spectra that you will get, that will be pure vibrational spectra. Okay. So pure vibrational spectra is also possible, but at that time, what is the condition? Along with electronic configuration remains the same, rotational state of the molecule should also remain the same. Now, as we have seen earlier, that the vibrational states are having larger energies involved as compared to rotational energy states. So, vibrational states are separated by energy interval of the order of zero point 0.1 electron volt, and therefore the vibrational spectra, because of the transitions, the lines observed in a spectra of a molecule, they will lie in near IR region. Near IR region. Okay, so let us go to the third type of the spectra, that is the electronic spectra. Electronic spectra. Okay, so transition between two electronic energy states of an atom in a molecule, that will result into a electronic spectra. So at that time, the molecule should not perform rotations, molecule should not have vibrational state, only there is a excitation of electron from a constituent atom to the higher level, or there should be a transition between the two electronic energy state of an atom in a molecule, that will result into electronic spectra. So this is just like a atomic spectra also. And you know that the energy separation between the electronic states, they are having higher energies as compared to the earlier two uh, type of spectra we have considered, that is the rotational spectra and rotational vibrational spectra. So the energies involved here are between 1 electron volt to 10 electron volt. So it is quite larger. Therefore, the spectral lines appears because of the transitions among these energies levels because of electronic excitation. They will appear in either visible or ultraviolet region of electromagnetic spectra. So, this is the third type, that is the electronic spectra. Now, we are going to start the study of the first type of spectrum, that is the rotational spectrum. Now, rotational spectra is very important in different applications or different fields of sciences. So, first of all, let us see what is its importance. First and very important thing, the rotational spectra can be used to distinguish the presence of isotope in a sample. So isotope means, you know, that the same element, that means the atomic number same but atomic mass number is different. That means there are different number of neutrons present in an atom. So such states are possible. So we call them as isotopes. So in a given sample, whether there are isotopes or not, that you can identify from the rotational spectra by studying the rotational spectra. Then you can also detect different isomers. In chemistry, you might have studied isomers. You know, the same molecular formula but different structure. They are called as isomers. So you can detect the isomers. How? Because the rotational energies are dependent upon moment of inertia. If the molecular formula is same but the structure is different, molecule structure is different, then there will be a different moment of inertia because of rotational motion involved for the molecules. And if the moment of inertia is different, even though molecular formula is same but structure is different, then in that particular case rotational energy state should be different, and from that you can identify the presence of isomers. Then chemical examination of interstellar space. So you know that we are always in search of presence of certain molecules in the interstellar space in order to identify or in order to investigate whether the life can be possible on different planets. So, for example, we are sending satellites to investigate whether oxygen is present or ammonia molecule is present in an interstellar space. That type of chemical examination is possible by studying the rotational spectra. Okay. Then to predict temperature of interstellar material. So by studying the transition among the rotational levels intensity of these lines because of rotational spectra, if you study, then you can predict the temperature of interstellar material also. So these are some important applications, you can say, rotational spectra. So this is very important. Now, two important points regarding rotational spectra is that only the molecules having permanent electric dipole moment can give rise to pure rotational spectra. This is very important. So molecules you can classify on the basis of their electric dipole moment. Some of the molecules, they may not have the permanent electric dipole moment. So such molecules will not show pure rotational spectra. So which molecules show? Only having permanent electric dipole moment. For example, HCl, HBr, HI, H2O. So these kind of molecules, they show rotational spectra in infrared region. Now, after this, in the last part of this lecture, we are going to study rotational energy levels of rigid diatomic molecule. So, molecular spectra is quite complex. So, to begin with, we shall consider an example of diatomic molecule only. Diatomic molecule, you know that in a molecule where two atoms are involved. Okay, this is the first atom and this is the second atom. So, I have used the word rigid here. Okay, rigid diatomic molecule. So what do you mean by rigid? Rigid means the distance between these two atoms, it is not changing at all. It is constant all the time. Therefore, it is a rigid diatomic molecule. Okay. So that means there are no vibrations involved. You can see here. Okay. So in order to study rotational energy level, we have seen earlier two conditions. Electronic configuration should remain same. That means the electron of these atoms and the electron of this atom should lie there in their ground states only. Okay, then that means their original orbitals only. Then second condition, there should be no vibrational states of these atoms about their mean position. So only possibility that they can have the rotational motion. So let us consider this diatomic molecule. The first atom, suppose having mass m1, this green one, and second atom has mass m2, this red one. The distance, equilibrium distance between these two atoms from their centers, you can say that is r0. And if you consider this as a bond between them, and this is a bond axis, imaginary line shown here between the two atoms. If you consider the center, okay, so you can call this as a center of mass. So in terms of classical concepts of physics, this is a two body problem. This is first particle, this is second particle. In fact, they are atoms, but you can treat them as a particles. Okay, so these two particles having certain masses m1 m2, so there may be some center of mass of this system. So let us assume that here is the center of mass, and you can assume an axis passing through the center of mass. So any motion, rotational motion about the center of mass, that will result into some rotational states of this molecule. So we shall consider the axis which is passing through the center of mass and normal to this bond axis of this molecule. So that will be the rotational motion of this diatomic molecule. Now the distance of the center of mass and the first atom, suppose R1, and the second atom, that is R2. Okay, so R0, you can say this total distance, that is R1 plus R2. Suppose this is equation number 1. Now, according to definition of the center of mass, you know that the M1 R1, that will be equal to M2 R2. So the center of mass is symmetrically placed here. So M1 R1 is equal to M2 R2. Suppose this is equation number 2. Now, the moment of inertia, according to the definition of moment of inertia, you can write the formula I is equal to M1 R1 square plus M2 R2 square. M is the mass, R1 is the distance from the axis of rotation. Okay, axis of rotation is passing through the center of mass, you can see here. Okay, so R1 is the distance. So M1 R1 square plus M2 R2 square, that is the moment of inertia. Suppose this is equation number 3. Now using equation 2 in equation 3, okay, M1 R1 is equal to M2 R2, we shall use here. Now equation 3, where you can write M1 R1 square, you can write as M1 R1 into R1. Okay, but M1 R1 you can replace by M2 R2. So same thing I have done here, M2 R2 into this one R1. Similarly, the second term you can replace by M2 R2 into R2. So M2 R2 replaced by M1 R1. So M1 R1 into this one R2. So I is equal to M2 R2 R1 plus M1 R1 R2. So you can take this particular R1 R2 common. So I will be equal to R1 R2 in bracket M1 plus M2. Okay. So from equation 1 and 2, equation 1, that is R0 is equal to R1 plus R2. Earlier we have seen. And equation 2 is this, M1 R1 is equal to M2 R2. So we can substitute here for R2 here from equation 1. So from equation 1, which is R0 is equal to R1 plus R2. So R2 will be equal to R0 minus R1. So you can replace R2 by R0 minus R1. So M1 R1 is equal to M2 in bracket R0 minus R1. So now if you multiply this, M2 R0 minus M2 R1. So minus M2 R1, if you take to the left hand side, that will be M1 R1 plus M2 R1. And R1 you can take common. So M1 plus M2 into R1 and is equal to M2 R0. So R1 will be equal to M2 upon M1 plus M2 into R0. Suppose this is equation number 4. So we have defined the value of R1 by using equation 1, 2 and 3. Similarly, you can perform the same type of operations to define the value of R2 also. So R2, if you perform the same operations, you will get R2 is equal to M1 upon M1 plus M2 into R0. Suppose this is equation number 5. So using these values of equation 4 and 5 in equation 3, equation 3, you know that is I is equal to R1 R2 in bracket M1 plus M2. We have defined earlier. Okay. So I is equal to R1 R2. You substitute these values R1 and R2. So this is R1, this is R2 into M1 plus M2. Okay. So R0 into R0, R0 square. M1, M2. And this is M1 plus M2 into M1 plus M2. That is M1 plus M2 square. And one of these will get cancelled. So in the denominator we have M1 plus M2. So finally you have an equation for moment of inertia. That is I is equal to M1 M2, this M1 M2 upon one of these get cancelled, simply remain one M1 plus M2. So M1 M2 upon M1 plus M2 into R0 square, this R0 into R0. Okay, this is the moment of inertia of this rigid diatomic molecule about an axis passing through the center of mass of this two body system. Now you can replace this term by mu. Let us replace this term by mu. So I will be equal to mu R0 square. Now you can consider here the two body system is converted into one body system, where mu represent the mass here of this system. So it is called as the reduced mass of the system. Okay, as if a single particle of mass mu is rotating about an axis which is at a distance r0. Okay, which is at a distance r0. So that is what we have converted a two body system into single body system. So if the molecule is rotating with angular velocity omega, then classically you know that the energy is given by E is equal to 1/2 I omega square. What is I here? It is the moment of inertia, and omega is the angular velocity. But angular momentum, according to classical physics, angular momentum L, that is equal to I into omega. So if you take a square here, so L square will be I square omega square. So you can replace this term by L square. So I square omega square divided by I. So E will be equal to L square upon 2I. This is equation 7. But according to quantum mechanics, the angular momentum is defined as, earlier we have seen this equation, okay, while studying the one valence electron system and two valence electron system and the spin orbit interaction. So L is equal to under root of J in bracket J plus 1 into H upon 2 pi. So if you substitute this L value in the earlier equation, that is E is equal to L square upon 2I. So L square, this square, so what will be that? J in bracket J plus 1 into H square upon 4 pi square. So if you substitute this L square and divide it by 2I, so it will be H square upon 2I. Therefore, 2 into this 4 pi square. So 8 pi square into I and square of this, that is J in bracket J plus 1. So this is the final equation which represent the energy of the energy level, rotational energy level. And here remember, J is the rotational quantum number. That means these energy levels are also quantized, and depending on the value J, that is equal to 0, 1, 2, 3, so on, the energy level value will also change. So that will actually represent the rotational energy state, and this equation is very important for us. So we can summarize that the rotational energy of a rigid diatomic molecule is quantized, and the rotational energy depends upon the moment of inertia of a molecule, that is on mass, shape and size. How? You can see here the rotational energy is inversely proportional to I. Okay, it is inversely proportional to I. And what is I? It is the moment of inertia, and moment of inertia of a particular molecule, it depend upon which particular constituent atoms are involved, what is their masses, then what is the shape of the molecule, what is the size of the molecule. All that will decide the uh, moment of inertia of the molecule. So rotational energy level, they depend upon the moment of inertia of the molecule, and they are also quantized. So these are the two important conclusions. So in short, the summary of this lecture, I can say the molecular spectra are more complex than atomic spectra. Then there are three types of spectra: pure rotational spectrum, rotational vibrational spectrum, and electronic spectrum. And finally, rotational energy of a rigid diatomic molecule is quantized, and it depends upon moment of inertia of a molecule. And in the next lecture, we are going to study about the rotation about a bond axis, whether the rotation about bond axis for a diatomic molecule are possible or not, and the actual spectra of rigid diatomic molecule we are going to study, because the only energy level equation we have derived here, we are going to study the actual spectra next time. And these are some additional references. If you want to study more detail about the molecular spectroscopy, these two references are important for us. These are available in our library. First one is Fundamentals of Molecular Spectroscopy by C.N. Banwell and E.M. McCash. And second one, that is Molecular Structure and Spectroscopy by Arul Das.